So the chapter ends, this last section 9.6, talking about situations where samples of gas might not behave as an idealized theoretical gas. So when does it occur that real gas measurements do not agree with the ideal gas law? So this non-ideal gas behavior is found at extreme conditions where the pressure of a gas is forcing these particles to come really close together so that they cannot be said to be just little tiny dots that are whizzing around completely apart from each other. That's what our theory is predicting. That's what our calculations are based on. A lot of times it's fairly accurate, but in extreme conditions that kind of breaks down. And we can measure how much it's breaking down with this compressibility factor, this Z. And that is a measurement of the real volume that a gas takes up, the measured volume, versus the volume that is calculated using the ideal gas law. So if the real volume matched the ideal gas volume, then these would be equal and Z would be 1. So if Z is 1, then it's equal to what you calculate with the ideal gas. If Z is less than 1, then the actual volume you measure is smaller than you expect. And if it's more than 1, then the actual volume you measure is larger than what you'd expect, what you've calculated with the ideal gas law. Let's take a look at this chart from your textbook that shows this value Z, this compressibility factor, over a range of pressures. So remember, if a gas is acting like an ideal gas, then the Z should be 1 no matter what, because the volume is the same as the calculated volume. If it drops below 1, then that's a sign that the volume is less than the calculated volume, and when it's above 1, the actual volume is larger than the calculated ideal volume that the gas should take up. So we see a lot of gases being lower than the calculated value at these fairly high pressures. I mean, these are high pressures, 200 atmospheres. Remember, 1 atmosphere is what we experience walking around. So we're talking about 200 atmospheres, up to about 400 atmospheres in this range. We have the volume being smaller than what we would calculate. And that is due to the interaction between the gas molecules. When you start pressing them close together at these pretty high pressures, then the gas molecules encounter each other more frequently and do show some attraction to each other. So an exception to this is hydrogen. So hydrogen, we have just such a small molecule and a nonpolar molecule that it does not really have much of a surface to be attracted to other molecules. But we do have some, especially with the larger molecules that have larger surface areas, they are able to approach each other and attract each other. Then as we get even more extreme with the pressure, so we get to 500-600 atmospheres, by this point, all of these gases have a larger actual volume than the calculated volume. And this is a result of the fact that the calculations, the ideal gas, does not take into account the fact that a molecule of gas itself has a volume. We're just talking about the volume of space that these invisibly small theoretical dots are whizzing around in, and we don't really take into account the volume of the molecule of gas itself. And normally that's fine, but then when you get to these really high pressures, then you're squeezing these molecules so close together that the actual space that the molecule takes up starts to make a difference. And so the real measured volume of the gas is larger than what the calculated theoretical volume would be. So down here at these high pressures, we have the attraction between the molecules, making the volume be lower than our calculated volume. And then at extreme high pressures, we have the volume of the gas molecule itself skewing the behavior of the real gas away from this ideal gas behavior. So there have been some modifications to the ideal gas law to make the calculations match more closely with what you really measure. And one example that your textbook gives, or the example that your textbook gives of one of these equations that tries to take reality more into account at these extreme conditions, is the van der Waals equation. We have a couple of correction factors that are put into this equation. A correction factor A that is based on the molecular attraction that gas molecules can exhibit, and a correction factor B, which is the volume of the gas molecule itself, which is another thing that can start to come into play at these extreme conditions. These values for A and B are specific to the particular gas that you're dealing with, because they all have a slightly different molecular size, molecular volume that they're taking up, and a slightly different molecular attraction. And so A and B have to be tailored to which gas you're talking about. But other than that, we can just kind of put those into this equation. So we'll just try one problem down below with the situation where oxygen gas is at a fairly high pressure, a fairly small volume, and we will do the calculations twice. We'll do once with the corrected van der Waals equation and once with the uncorrected ideal gas law to just compare what different answers we come up with. So first, let's calculate this using the ideal gas law. So the ideal gas law, PV equals nRT, would have the pressure being equal to nRT over V. The number of moles is 8.77 moles. R is 0.08206 liters atmospheres per mole Kelvin, and the temperature is 313 Kelvin, and the volume is 4.4 liters. So the moles cancel, the liters cancel, and the Kelvin cancel, and we end up with atmospheres. This ends up being 51 atmospheres. There's really only two significant digits, so I'll underline that one. And we'll go ahead and move this up here so we can do a calculation with the other van der Waals equation. So let's go ahead and look at this van der Waals equation and solve that for the pressure. So the first thing is to divide both sides of this equation by V minus NB. And that leaves us with P plus AN squared over V squared on the left side of the equation and nRT over V minus NB on the right side. Then to get P alone, we take that nRT over V minus NB and we subtract the AN squared over V squared. So we're subtracting that from both sides of the equation here. All right, when we insert all of these values into the equation we've just come up with, N is 8.77 moles. So we have R being 0.08206 liters atmospheres per mole Kelvin, the temperature being 313 Kelvin. Then we have volume 4.4 liters minus NB. So here's the N, 8.77 moles. B for oxygen is 0.0318 liters per mole. So this mole times liters per mole cancels these two moles, and we're going to have this amount in liters, and this term is going to also be liters. Then over here we have the AN squared over V squared. A is 1.36 liters squared atmospheres per mole squared, so that's this over here. And then we have N, which is 8.77 moles, that's going to be squared. And then we have the V, the volume, which is 4.4 liters, and that's going to be squared. So then this liter squared will cancel with this liter squared. The mole squared will cancel with this mole squared. and we'll have a term with atmospheres over here on this side. This is also going to end up with atmospheres because this moles cancels this mole, and this Kelvin cancels this Kelvin, and this whole thing is going to be liters, and that's going to cancel with this liters as well. Alright, so let's clean up some of these terms over here. 8.77 times 0.08206 times 313 comes out to be 225.26 liter atmospheres. And this 4.4 liters minus the 8.77 times 0.0318 comes out to be 4.121 liters. And then this over here, the 1.36 times 8.77 squared divided by 4.4 squared comes out to be 5.40 atmospheres. Alright, and we should just keep track of our significant digits here. This one only has 3 significant digits, and this one only goes 1 past the decimal because of the subtraction, so it only really has 2 significant digits. So we have 2 significant digits here and 3 here. Again, this is going to be based on place value because now we're subtracting, so we're going to have it at the ones place, and this comes out to be 49.26, again just known to the ones place. So we have an ideal gas answer. When we use the ideal gas law, we come out with a pressure of 51 atmospheres. When we use the van der Waals corrected gas pressure, it comes out to be 49 atmospheres. So slightly different. We're in that range, remember, with the Z's. We have the value that the ideal gas calculates. When we're in this lower range, so below about 400 atmospheres, we're going to be a little bit lower in the pressure and the volume because of the attraction between the molecules. And then if we went up to a much higher pressure range, we would have a higher value for the corrected pressure or volume that we are working with than what the ideal gas would predict.